Hi, this is Mrs. Basin, and today we're going to talk about reaction rates. So the reaction rate is the change in concentration of a reactant or product over time. So there's two different ways that you can look at a reaction rate. You can look at what's called the average rate, which is the change over a given time frame, which is what we are going to mostly focus on. So to calculate an average rate, you take the change in concentration divided by the change in time, and you would be given a data table that would have that information on there. An instantaneous rate would be a change at a specific time. So to calculate that, you would take the slope of a line tangent to that specific time. So for the instantaneous rate, all you have to know is how to figure out an instantaneous rate. We're not actually going to calculate instantaneous rates. So if you look at the diagram on the page, you can see this is a very simple reaction of A as a reactant changing to B, the product. So A is changing to B. The purple substances are A, and then the green substances are B. So you can see when you start out, you have all A and no B, but then as the reaction proceeds, the concentration of A decreases, and then the concentration of B increases. The other thing you notice too, that this is not a steady decrease. So the change kind of slows over time. So it's pretty steep in the beginning, but then it kind of slows out. So you saw that a little bit yesterday when you did some of those graphs for the light stick activity we did, where you saw that it wasn't going to reach exactly zero. It was just slowing down over time. Now in this case, it does look like it reaches zero, but we'll talk more about that later. Okay, so when we do these mathematically, this is how this would work. So this particular example problem is not in your packet, but I added this in because this is something you're going to have to do when you go to do the practice. So if you want to write this in your notes, you can. If you just want to use this as a reference and come back to the notes for that, you can do that too. So this is another example. So you can again see the H2 and the I2 are being added together to make HI. And in this case, all we're being shown is the H2 concentration. So we're not seeing the I2 concentration on this particular graph. It's just focusing on the H2. And then you can see the HI is being formed. So again, the H2 is decreasing over time, and then the HI is forming. So for this one, we have a data table, and the part of this data table that we're concerned with is just these first two columns. So you can see what's happening to H2 as time progresses. So first of all, we do notice that it's decreasing, and then you can also see that it's decreasing pretty significantly in the first few seconds, but then it slows down as it gets towards the bottom or towards the end of the time that's given here. So as we're looking at this first question, it says, what happens to the rate of the reaction as it progresses? And like we just said, we would say that it slows down. Okay, and the reason that happens is because you're running out of reactants. So at the beginning, there's a lot of reactants available. So they're going to react very readily because there's a high concentration of them, and it's very easy for them to run into each other and have enough energy to be able to react. But as those reactants start being used up, there's not as many, so they're not as likely to run into each other to produce those products. And again, we'll do some more modeling with this later on. So that is why that reaction slows down as time progresses. So then the second one, we're actually going to do a calculation for. So if I want the average rate, that was that first rate we talked about on the previous slide. So the rate is going to be the change. So remember that Greek sign delta means change in concentration over change in time. And if you remember from before, the brackets just stand for concentration. That's why we put concentration in brackets. The other thing to remember is anytime we calculate that change, calculate that delta, it's always final minus initial, because you're going to see some positive and negative values show up here, and that relates to whether a reactant or a product is decreasing or increasing or disappearing or appearing. So our first thing is our concentration. And again, we're looking at the difference between 50 and 100. So 100 is down here, and there's our concentration of H2. And then 50 is about in the middle here, and there's our concentration of H2 as well. So to figure out the change in concentration, I'm going to take the final value minus the initial value. So I'm going to take that 0.135 minus 0.368, and the units on that are molarity. So since these are concentrations, you're going to see mostly we're going to use molarity units here. And then for the bottom part of this, we need the change in time. So final was 100, initial was 50. So 100 minus 50. So then our change becomes minus 0.233 or negative 0.233 over 50. Now what that negative sign is telling us, again, it's kind of a directional indicator here. So if a rate is negative, that means that the concentration is decreasing. If the rate is positive, that means that the concentration is increasing. And again, on the next slide here, we'll see that a little more. So when we solve for that, then our rate is going to be negative 0.00466, and these will have units. So the units are going to be dependent on how the data is given. So in this case, the concentration unit was molarity, the time unit was seconds. So this would be molarity per second. So the rate is decreasing at a rate of 0.00466 molar for every second that passes for that particular reaction. Okay, so those are the ones that you'll have to know how to actually calculate. For this instantaneous rate, to figure that out, we would say, and that's kind of what these are showing here, so we're not actually going to calculate those, but we would take that tangent line to whatever that instantaneous rate was that we were trying to calculate, and we would solve for the slope of that line. We are not going to do those calculations, but if we were going to do that, that's how you would do that calculation. Okay, the next thing we're going to look at in this first section here is looking at how the stoichiometry can relate to the reaction rate. So for this one, if you're generalizing a reaction, and we're just using A's and B's for the reactants and products, the lowercase a's and b's are the coefficients, and then the capital A's and B's and C's and D's are the reactants and products. So when you're relating the reactants to the products or a reactant to another reactant, this is the format we're going to use. So this is 1 over the change in concentration of A over lowercase a times the change in time. This one is negative, again, because it's a reactant. So over here we have our reactants. So the reactants are going to have a negative sign, and again, that just tells me that the reactants are decreasing in concentration. And then on the other side, we have our products, and our products, it's not listed here, but those are positive values, so you don't have to write that. And that means that the products are increasing in concentration. So both of the reactants, here's our B, so change in B over lowercase b, change in time. So again, these lowercase ones are the coefficients. And then our products, change in C over C change in time, change in D over D change in time. Okay, that's a little confusing, so on this next example, we're going to clear that up a little bit. So this is a reaction for hydrogen peroxide reacting with iodine. So what we're going to do first here is show the relationship between all of the reactants and products in the reaction. So before we start the problems, and on your sheet here, again, I added this piece in here just so we could kind of clear up that previous discussion we just had. So you may have to put this at the top of your page instead of following right along with the notes. So we're showing the relationship between all of the reactants and products in this reaction right here. So what we would do first, we would say the change in concentration of H2O2 over change in time, okay, and then this is going to be negative because it's a reactant, and in front of the change in time there's a 1, which we don't have to write. That's equal to, also negative, change in concentration of I minus over 3 change in time, and that 3 comes from the coefficient, and that's also equal to change in concentration of H plus, which is negative because again, still we're on the reactant side, over 2 change in time. Okay, so those are my reactants. And now I'm going to add in the products. I'm still setting all of these things equal to each other to show that there's a relationship between any two things in this balanced equation. These are going to be positive now. So I'm going to put the positive there just as a reminder, but you don't have to put the positive there. Change in concentration of I3 over change in time because the coefficient is 1. And then again, change in concentration of H2O over 2 delta T. Okay, so that shows the relationship between all of those reactants and products. So you're not always going to have to do that, but I wanted to start with that so we can kind of see where these other values are coming from. Okay, so then for this one, to calculate this rate, since we have the relationship for I minus, which is this one right here, this is I minus, the change in concentration of I minus over 3 delta T, that's the relationship. So it tells me that it drops from 0.86, or from 1 molar to 0.86. So again, final minus initial is that change. So 0.86 was the final, minus 1 was the initial, over, and I'm going to leave this coefficient in here because this is how I'm getting this rate for this particular problem, times change in time. Change in time, it told me, was 10 seconds. Okay, so then that tells me that this rate would be negative, again, because this is a negative, this is a reactant, 0.0044. The units are molarity per second. And then if we wanted to, we could put this into scientific notation. So 4.4 times 10 to the negative third molarity per second. Okay, so now it says determine the rate of change in the concentration of H plus during this time interval. So since I have this balanced equation and I have the relationship between these two substances in this balanced equation, and I know the value for one of them, I can use this relationship to solve for the other one. Now, when I'm solving for a rate of change, I'm solving for the change in concentration over the change in time. So what that means is when I'm solving for this, I have to get rid of this 2 that's in front of the change in time. So I'll set this up so we can see what this looks like. So we know that the change in I minus over 3 delta T is equal to the change in concentration of H plus. And I'm going to ignore the negative signs for right now. Okay, so this value here is what we're going to put in place of this. So we're going to say, and like I said, I'm going to get rid of the negative signs just for now. 4.4 times 10 to the negative 3 molarity per second is equal to the change in concentration of H plus over 2 delta T. And like I said a minute ago, when I'm solving for the rate, this is the rate. So that means for me to solve for the rate, I have to move this 2 to the other side. So the rate is 2 times, for the hydrogen, it's 2 times the rate of the I minus. And that 3 is not in there because that's already been taken care of when we calculated that rate in the previous problem. So the change in concentration, or the rate, I'm running out of room here. So the rate for the change in concentration of H plus over time is equal to this value times 2. So that, putting that 2 over there, it gets rid of it. So that becomes 8.80 times 10 to the negative third molarity per second. And again, this would be negative because this is a reactant. So this is how you can solve for rates using stoichiometry. So this is what you're going to practice today. And then tomorrow we'll come back and look at how we can actually solve for what are called rate laws. The one other thing we want to talk about today is how they actually gather this rate data. So there's a couple different methods. The polarimetry is one way, spectroscopy is another way. If you, last year you might have used a spec 20 or even the specs with the Vernier equipment in AP Bio, because what that's doing is it can measure how a reaction is changing by looking at the change in the color or the concentration of it. And then if it's a gas, you can also measure a change in concentration with a pressure measurement. So we'll do at least 1, maybe 2 labs with this unit where you'll get some experience with some of these. But this is where this data comes from. Okay, so what you're going to do then is you're going to work on the practice, and the practice is called reaction rates. So it's the first practice sheet in there. We did do a little bit of the first page of this in Honors Chem, so some of it might be a little bit familiar. This stuff we just got finished doing is new stuff, so the stoichiometry stuff is new. So do the best you can with it. The answer key is posted. If you need help, send me a message on Google Classroom and I can Zoom with you if you need help working through a problem or you need me to explain something. I can do that while you're working.